Welcome back, Geos406 students. So this homework module, actually, I really like this one. It's pretty fun. And again, it's based on the modules developed by Chuck Connor, University of South Florida, for this physical volcanology collection that I've been using for this course. I made some modifications to the questions in particular, but I've largely left this one in its original format because I think it's a really, really great homework problem set that gives you some experience modeling lava flow behavior for basalt lava flows, and then using that information to make some hazard estimates and forecasting of lava flow lengths. Okay, so what is the relationship between lava flow length and effusion rate at Mount Etna, but also expanded to include a little bit of planetary volcanology as well as some problems centered on Hawaii? So you're going to use some data from active lava flows to formulate a relationship between the effusion rate, so the rate at which the lava is coming out of the volcano, and ultimately how far the resulting lava flow will travel based on that effusion rate. So what are lava flows? Well, they're streams of magma that erupted from a volcano without explosions typically. Some fountain-fed lava flows are fed by Hawaiian lava fountaining, but other lava flows just emanate from the volcano quiescently without any fragmentation. I have a beautiful photo example here of an andesitic lava flow from Canaga volcano, and this was taken by Michelle Coombs, one of my AVO colleagues at USGS. So lava flows are effusive flows. So when the magma reaches the surface, it exits as a bubbly flow. And we know that lavas erupt on Earth, Mars, and even Io. So they're planetary scale features. Planetary geologists and volcanologists are very interested in not just the lava flow features they see from satellite images from other planets, but also analogs on Earth that they can use to model planetary scale processes elsewhere in the solar system. So lava flows are different from lava domes. Lava flows usually represent lower viscosity magmas, so like a basalt. They flow away from the vent and they travel sometimes long distances. Unlike a lava dome, which is very viscous and silicic and sticky and thick, the lava domes don't travel very far away from the vent. So lava flow length depends in a very simplistic way on the discharge rate of lava at the vent and the physical characteristics of the lava, the topography onto which the lava flows, and the environment of the flow, whether it erupts underwater or on an Earth atmosphere or a Venus atmosphere or a Mars atmosphere. All of those things are important. So again, lava flows are planetary scale features. Here's some really cool images from NASA and JPL, and they show lava flows in different parts of the solar system. So we have lava flows on the surface of Io, which is one of Jupiter's moons, and that's this right-hand image here. You're actually going to use this image and the information given in this caption here for part of your homework assignment. We also know that there are lava flows on Venus, and this lower image here shows some of those flows. The surface of Venus, it also has relatively few impact craters, so it's considered to possibly be covered by relatively young lava flows. But we know from the morphology of these flows and the craters they seem to emanate from that there are indeed lava flows. Lava flows can be really hazardous. Typically, basalt lava flows go slow enough that people can get out of the way. They're very damaging to property, though. However, there have been instances where lava flows actually were deadly. And so it's a really, really crucial hazard for volcanologists to understand and be able to model accurately so that you can warn people in the event that a lava flow is coming their way, basically. So in 2002, the eruption of Nyiragongo volcano. It's a shield volcano in the Democratic Republic of Congo. In a few hours, lava flows from this volcano did tremendous damage and resulted in more than 40 fatalities. So here's a map image showing the path of the lava flow as it flowed through the city of Goma in the DRC. And here's a photo on the lower left showing that lava flow flowing through the city. You can see a building in the background. So this lava flow moved very rapidly, greater than 10 meters per second, which is fast for a basaltic lava. And the reason is because it's an alkalic basalt. It's a very low viscosity form of basalt. The other reason this flow was so destructive is that it emanated from fissures that opened up just outside of town. And the third reason is that in this part of the world, they're not as fortunate as some other first world countries are. They don't have access to really good high-tech volcano monitoring. So there was really no warning for this fast-moving lava flow flowing through the city of Goma. Okay, so this module is based upon observations of lava flows from Mount Etna. There's a video that it's going to be hard to play it through the PowerPoint slide, but it is uploaded into Blackboard and you can watch it on Blackboard. So we really want to know, given some observations of how fast the lava is coming out of the vent of the volcano, we want to actually have some way of estimating how far that lava flow is going to go so that we can properly warn people about the hazards that are coming their way from the lava flow. So the observations from Mount Etna were taken and used in this module by Chuck Connor to come up with a way to teach you how to model lava flow lengths from a fusion rate. So you can learn how to use this information for volcano hazards purposes. So the problem is, what is the relationship between lava flow effusion rate and length? And can we apply this model to estimate hazards and run out lengths of lava flows down the flanks of the volcano? Lava flow dynamics are really complex, so we're going to use a pretty simple model to estimate the flow length from a fusion rate simply. But there are other factors involved that would be really important if you were going to develop a more sophisticated model than the one that we'll use in this class. So flow morphologies, whether you have a smoothly flowing lava flow or a broken up, rubbly lava flow, that's important. Emplacement mechanisms, that's where the lava flow settles and flows. The rates of cooling, their interaction with the surrounding environment and topography, and many other factors. So here we're only going to consider one variable, effusion rate, and its relationship to lava flow length, and a very cursory, sort of simple first-hand model. So how are you going to solve this problem? So you're going to be given some information from Mount Etna about effusion rate and lengths of lavas, and you're going to develop a statistical model for these lava flows. That's very important. Remember that this model is based on lava, not pahoehoe. You're also going to use this model to apply to lava flows on Io to estimate effusion rate. And you're also going to try out your solution using data from two other volcanoes, Mauna Loa and Kilauea in Hawaii. I'm going to make a note here, and hopefully you will remember this for some of the questions in your module. Mauna Loa and Kilauea often don't produce solely lava. Sometimes it's pahoehoe. So consider the application of this model developed for lava flows to volcanoes that might have produced pahoehoe. The differences, there might be differences. So you're going to need to gather data on lava flow length and effusion rate, although that'll be given to you for this homework assignment, except you're going to be asked also to develop your own effusion rate based on the video that's linked in Blackboard. You'll find a best fit linear model for these data, so you can have a line fit, and then the model that you derive from that line will give you a way to estimate lava flow length from effusion rate. Simply, you'll calculate maximum potential lava flow length based upon the Kilburn equation, which is a physical model of lava flows. And then you're going to compare some statistics and model results. And then I'm going to ask you to apply your knowledge for some simple hazard scenarios at Mount Etna and in Mauna Loa and Kilauea in Hawaii. All right, so this slide is giving you the parameters that you need to estimate lava flow lengths, and it's also giving you the Kilburn equation. So this equation here, the maximum lava flow length is equal to the square root of 3 times epsilon times big S divided by rho g kappa times q to the 1/2. So what does all this mean? So this is the Kilburn equation. It was developed between observations of mean effusion rate of lavas during an eruption and the maximum potential flow length for those lavas, which depends to a great extent on the mechanical and thermodynamical properties of the lava crust. So if you remember from the lecture, remember what a lava flow looks like as it's flowing, and that's the situation you're modeling here, the thermal properties of that brittle basaltic lava crust. So L sub m is the maximum potential lava flow length in meters. You're going to be calculating that parameter. Epsilon is extension before failure, so that's the measure of how far the basaltic crust of the lava can be pulled and stretched before it breaks during that lava flow. It's dimensionless. The value is 10 to the minus third for a chilled crust. Big S is tensile strength of the crust. It's a measure of how hard it is to actually pull apart the basaltic crust of the lava before it breaks. It's given in units of Pascal, and it's got a maximum of 10 to the 7th Pascal for a chilled crust. That's actually kind of a lot. Rho is density of the lava crust, not the flow, so it's just the crust in kilograms per cubic meter. So this is around 2,200 kilograms per cubic meter for basaltic lava flow crust with 20% vesicles. G is the gravitational acceleration constant in meters per second squared. That's 9.8 meters per second squared. Kappa is bulk thermal diffusivity. It's a measure of how long it takes heat to move through the crust by conduction. It's given in meters squared per second. It's a diffusion parameter. And the value you'll use is around 4 times 10 to the 7th minus 7th meters squared per second. So this is a limiting value. Might be lower for a vesicular crust, but you're going to use this 4 times 10 to the minus 7th for your models. Q is mean volumetric rate of lava flowing from the vent in meters cubed per second, and this is a parameter that you will be given in your data set. So again, data on the mean effusion rate during the eruption and final lava flow length will be given to you, and you're going to be asked to fit simple linear model through the given data. So I've shown an example here from the Mauna Loa data. If you exit the slideshow view of this PowerPoint and double click on this graph, you will also pull up the embedded Excel file with your data sheets in it. That Excel spreadsheet is also available in the course materials section of Blackboard. You'll need that for your homework calculations. So you're going to develop an empirical linear relationship between lava flow and effusion rate and the lava flow length. And then you're going to calculate lava flow length from effusion rate using the Kilburn equation as a second model. So in this slide, I'm showing you an example of what your first set of calculations should look like. So you're given lava flow length and you're given volumetric effusion rate from Mount Etna. You're going to start with the Mount Etna data. So go to that sheet in your worksheet from the Excel spreadsheet in Blackboard. And you're going to calculate the log of the length and the log of the effusion rate. So just take the log of the lava flow length in kilometers and the log of the volumetric effusion rate. You're going to notice here that you've got a little bit of a difference in units, log lava flow length in kilometers on the y-axis versus log effusion rate in meters cubed per second on the x-axis. You can formulate your calculation and then check against this example to make sure that your calculations are correct. Then you're going to plot log lava flow length versus log effusion rate, and you're going to fit a linear trend line to it. And you're going to come up with the line fit, which is y equals mx plus b. In this case, it's y equals 0.52x minus 0.1497 with an r squared coefficient of 0.94. So these are the things that you're going to want to do with your first setup. The second thing you're going to do is use the Kilburn equation, which was shown to you on a prior slide, with these parameters also given to you on that same slide. For epsilon, s, rho, g, and kappa, these are the parameters you're going to use. You're going to use the Kilburn equation to calculate maximum lava flow length Lm in kilometers. And then you're going to take the log of the lava flow length in kilometers and you're going to plot it alongside your Mount Etna data as shown here. So the Mount Etna data is shown in blue. The Kilburn equation calculation is the line shown with the the magenta colored squares. You can use this example to check your calculations of the Kilburn equation and make sure you're getting the right numbers from your spreadsheet. After you've modeled the Mount Etna case, you're going to be asked some additional questions. You're going to apply your model to estimating the effusion rate on Jupiter's moon Io, which lends it a planetary science aspect to this homework assignment. Then you're going to be asked to use some additional data from Mauna Loa and Kilauea volcano that's given to you in the spreadsheet. It's just in different worksheets. These data are provided by Chris Kilburn for this module developed by Chuck Connor. So you'll use the Mauna Loa and Kilauea data to answer some additional questions at the end of your homework assignment. So just for a background, you can see here for this end part of your homework assignment, the lava flow hazard map for Hawaii, for the Big Island. And this is very interesting and instructive because we know that in 2008 we had lava flows that opened up along the East Rift and they really caused a lot of damage. So this hazard map is pre-2018, but it shows you different hazard zones based upon the frequency of recent eruptions from Hawaiian volcanoes. Hilo is located here. It's in a moderately high hazard area and it's actually at risk from lava flows primarily from Mauna Loa. So this is a map that you're going to want to study for the last part of your homework assignment. Okay, so here's some instructions and summary. First, I'd like you to read this PowerPoint file completely because you're going to use it for the parameters and model equations that you need for this module. Next, read the homework document, the Word document that explains your assignment and gives you all the questions completely, so you know first what you're going to be asked to do for this assignment before you get started. You're going to need the Excel sheet that's given to you in Blackboard. It's also linked into this PowerPoint file, but if you can't access it from the PowerPoint file, it's in Blackboard as well, so you can download it from the course materials area. That Excel sheet has the Etna, Kilauea, and Mauna Loa data linked into it that you'll need for your calculations. The constants you need for the Kilburn equation, as well as the equation itself, are given to you in this PowerPoint module. If you haven't noticed them in the prior slide, they're also given to you on slide 11 in the example spreadsheet in the green boxes. You're going to use the examples given on slides 10 and 11 in this PowerPoint file to help you set up and check your calculations. And if you get stuck, don't hesitate to ask me for help. And I really hope you have fun with this module. This is one of my favorites.